Hi, everyone. Welcome to another Buena Vista Museum of Natural History and Science Meet the Expert event. I'm Mark Hodson, a museum volunteer, and today we're here with Dr. Matt Herman. He will be examining whether earthquakes can be triggered by other geological processes or events, including other earthquakes. Dr. Herman is currently assistant professor at Cal State University at Bakersfield. He is particularly well qualified as he previously received a bachelor's degree in geology and physics from Amherst College, earned a master's degree in geosciences and a PhD at Penn State University, and has also performed postdoctoral work at Utrecht University in the Netherlands. During his time in the Netherlands, he and his wife made great use of Europe's excellent train systems and enjoyed many European countries. His interest in geology began his first year at college. Before that, he had been interested for many years in some of the traditionally more mathematics-intensive sciences such as physics, astronomy, and chemistry. All it took was enrolling in one geology class, and his focus shifted. He did retain his affinity for mathematics, as he is now a geophysicist. I would also mention that he enjoys playing and watching sports and pays close attention to NBA basketball. His own father has learned not to question Dr. Herman's mastery of the details of the National Basketball Association. Before we get started, if you enjoy today's event and you would like to see more content like this from the Buena Vista Museum, I invite you all to make a donation. You can donate to the museum anytime at buenavistamuseum.org/donate. I'll put that URL in the chat box. Please keep your devices muted, and if you have any questions during the presentation, please type them into the chat window. There should be a chat button on your screen. Just click that and then enter your question. We will address them at the end of the presentation. If you are unable to enter your question in the chat window, you're welcome to stay with us until we've answered the chat questions. And at that time, you may unmute and we will entertain your question. Without further ado, welcome, Dr. Herman.
Thank you for that really generous introduction. So I am a professor in the Department of Geological Sciences at CSUB, and I study earthquakes. So this is a topic that's near and dear to my heart. And studying earthquakes and studying geology has taken me all over the world, not just the Netherlands, all over Europe, all over some other places. It's been pretty exciting. And so actually in this talk, we're going to start in California, but we're actually going to go all over the world in some of the places that I've thought about before. Okay, so let's get started. There we go. Okay, PowerPoint works. Okay, so if you came to my last talk, this map of Southern California will look pretty familiar because I like to start with where we are actually in the world. And this map is showing the region around Kern County and Bakersfield. You can see the town of Bakersfield here. You can see the Sierra Nevada mountain range to the east. You can see the coastal and transverse mountains making the other sides of the valley. Out here far in the east, we've got the Mojave Desert, and of course that big city to the south, Los Angeles. So since I and probably many of us are here at Bakersfield, I highlighted the city with a big bold white rectangle so you can orient yourself. Now I have a question for people. Was anybody in or around Bakersfield on the 4th of July in the morning in 2019? Does anybody remember what happened? Okay, we got one thumbs up. Two. A couple of people, three. Okay, so a couple of people were here. I don't actually know if you can type in the chat or anything like that, but those of you who are giving thumbs up probably know what happened. And to bury the lead, why is this not switching? There was an earthquake at about 10:30 in the morning on the 4th of July, 2019. A magnitude 6.4 earthquake struck near the town of Ridgecrest, out here to the east of Bakersfield. Now, the United States Geological Survey, they have an ongoing project called Did You Feel It?, where they collect reports from anyone who experiences an earthquake. Now, if they're lucky, they get about 100 reports for an earthquake. That would be a lot of responses. This earthquake happened in California, where there's a lot of people care a lot about earthquakes. And this earthquake had almost 50,000 responses because people felt it all over California. This is a map here showing California, and each of these little colored squares represents an area where people reported feeling the earthquake. And you can see it's as far south as San Diego and as far north as Sacramento. People felt this earthquake. This means that the shaking from the earthquake was probably felt by several million people. Obviously, not all of them reported it, but a lot of people in California felt this earthquake, experienced this earthquake. And in fact, if you haven't posted your report to Did You Feel It, you can actually still go back today and say that you felt it, and your data will be added to this, this database. Okay, and this earthquake didn't do a ton of damage in Bakersfield. Bakersfield was generally spared, but it did do substantial damage, most of it right near where the earthquake occurred in the town of Ridgecrest. So you can see damage to the masonry in this building. You can see this mobile home is, unusable anymore. You cannot live in there. The books falling off the shelves. This is, substantial damage. All of these things take time, money, materials to fix. But so this is not great, but at least this is the end of it, right? This was the end of it. There was nothing more. No, not quite. At 8:30 the next night, a mere 34 hours later, an even larger magnitude 7.1 earthquake occurred in almost the same place. And although fewer people actually reported feeling this earthquake, only about 40,000 reports, it was felt probably over an even larger area by about 20 million people or so. Now, why would fewer people report feeling it? Well, maybe they reported a week later and they couldn't remember which one exactly they were talking about, or they're like, oh, I already reported an earthquake, I don't need to report a second one, things like that. But still, 40,000 reports is significant, and a lot of people felt this earthquake. Even in Phoenix, look over here, all the way in Phoenix. Okay, so this earthquake, again, despite its larger size, Bakersfield got through it with minimal damage, but Ridgecrest got hammered again, as did the nearby town of Trona and the China Lake Naval Air Weapons Station. And you can see, some of the damage here to things like convenience stores, to homes made out of bricks. This earthquake started some fires in homes. So, pretty substantial damage. Now, incidentally, that military station made studying these earthquakes really difficult. Because the military doesn't just let geologists, particularly geologists from universities, be like, hey, I'm going to walk through the base, I'm going to make some measurements, take some pictures, and just post them to the web or something. Military doesn't usually like that. But the military was really interested in understanding the event and the scope of damage and the potential for future earthquakes, because they got hit pretty hard. There was damage there. So there was this kind of weird situation where some government scientists were given clearance to make measurements, but they actually couldn't share the results completely with folks like me at universities. It was a weird situation. But anyways, kind of after the fact now, we've been able to compile a lot of these data sets and, say some interesting things about these earthquakes. But I digress. Okay, so there's two pretty large, widely felt earthquakes occurring in almost the same place within a day and a half of each other. Let's next zoom into this area where the earthquakes occurred a little more closely. Now I'm going to show you an animation of the earthquakes over about 2 days. This clip will start with the location. You can see right here, the initial magnitude 6.4 earthquake on the 4th of July, starting at 10:30 a.m. When I press play, you're going to see a bunch of little blue dots pop up. All of those are aftershocks, and aftershocks are just smaller earthquakes happening right after the first event. So let's roll the clip. In the minutes and hours right after the initial magnitude 6.4, we immediately see aftershocks popping off like crazy, tons of blue dots there. That's just like we expect. And you see, eventually they kind of slow down a little bit. Yes, they're still popping off, but there's fewer and fewer over time. That's exactly what we expect for this type of thing. Until right now. Then bang, the magnitude 7.1 earthquake hits on the 5th of July, and it sets off its own aftershock sequence in red. Okay, so two events close in time, close in space. In fact, these earthquakes were only 10 miles apart and only 34 hours apart. So it's pretty tempting to ask, are these two earthquakes related? Or more specifically, did the 4th of July earthquake somehow cause or trigger the July 5th earthquake to occur? Now, to address this question, we need to talk a little bit about what an earthquake actually is. And an earthquake is the sudden release of energy that occurs from slip along a fault. And a fault, what is a fault? It's simply a crack or a fracture in the earth. Now, here's a picture of the region just west of Bakersfield in the Carrizo Plain. So Bakersfield's about an hour to the right of this picture. And we can see here a very famous fault, the San Andreas Fault. It's a giant fracture in the earth. Now, if things were just sitting here, stagnant, we wouldn't have anything to worry about. We wouldn't have to be having this conversation about earthquakes. But there's tectonic plates on either side of the San Andreas Fault, and they're moving very slowly, but they don't ever stop. They move at about 40 millimeters or about 1.5 inches a year. So over 1 year is really not a lot, but you do it over 100 years and you can move quite a bit, 10, 20 feet past each other. The fault during this period is totally stuck together. It's like the two sides are glued together. That's because of friction. And I don't want to get too deep into friction, but you can think of them just being totally stuck together. So the rocks on either side, they build up energy, like stretching a spring or a rubber band. And at some point, the rocks build up enough energy that the force on the fault just breaks that sticking apart, and bang, the two sides just break past each other. That's the earthquake. So here's a little cartoon, kind of a bird's eye view of what's happening on the San Andreas. We see over time the plates move and those rocks bend and bend and bend and bend and then pop. So we'll see it go again, bend and bend and bend and pop. There's the earthquake. And we'll see it go bend and 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 pop. There's the earthquake. And this happens again and again and again and again. So we call this the earthquake cycle. For those of you who are scientists in the audience, this is your opportunity to ask me, okay, so what? Sure, there's an earthquake, but why should this earthquake make another one more likely to happen? To answer this question, I want to take you to another very common situation with the fracture between two blocks, a crack on your windshield. So, who has had a crack on their car windshield before? Okay, I got some thumbs up here. I suspect this is going to be a lot of people. If they haven't had it on their windshield, they've definitely seen it on somebody else's. So this is a video. Actually, there's not too many videos of cracks on windshields, except cracks on windshields getting fixed on YouTube. So I really had to dig for this. But here is a time-lapse video showing a crack growing across a windshield. So we can see this movie, the crack starts in the left side over here, and you can see it slowly go over to the right. And then sometimes it goes a little faster and it keeps going to the right, to the right, to the right. And it goes all the way over to basically the right side of the image. And yes, it's a time lapse, but you can get a sense that this is happening over a few minutes. So the crack starts over here on the left-hand side and extends all the way over to the right. Okay, here's another video, and mostly I'm showing this because this guy has what I think is the correct reaction to having a crack slowly growing on his windshield.
Oh gosh, that is not good. Crack keeps on getting bigger. I'm worried.
And so maybe it's a little tough to see, but that crack is also going from the right over here and spreading a little bit to the left. You can see it in real time here. Okay, this guy probably shouldn't be taking a video of a crack on his windshield while he's driving. That is not safe. I do not recommend that. So I do not endorse this guy's videotaping his crack, but again, it gives me a good video to show you for this talk. So in both of these cases, indeed, in most instances of cracks on windshields, the cracks grow by extending along their tips. So the first one we saw grew along its tip to the right. The second one we saw grew along its tip to the left. And we could ask ourselves, why do these cracks get bigger at all? But a slightly different question, one that connects back to our issue of triggering, is why does the existence of a crack tend to cause more cracking at the tip? After all, when your windshield is whole, it doesn't start randomly cracking. You got to start a crack somehow, usually getting hit by like a rock or something. But as soon as you start even a tiny, tiny, tiny crack, it's going to start growing, just like these ones did here. So why does one crack start off, growing and start cracking more? What's happening? We're going to zoom into the very tip of this crack here. And I've tried to show this in sort of simplified cartoon land here. So this is zooming into the tip of the crack. The gray stuff here is the windshield. You can imagine the windshield, the crack is breaking through the windshield here. Now what's happening? The crack is opening. So the two sides are actually moving slightly apart from each other. And what we're going to imagine is that we are standing on the glass, on the top side of the crack here. So, these are just cartoon images, but you can imagine that you're standing there and you're actually holding hands with the people on the crack next to you, okay? Now, in order to open this crack, you all take one step and you basically step in unison. You step as one, so everybody's happy and you're still holding hands. Yes, there's a crack behind you, but everybody next to you, you're fine, right? If you all hold hands and you take one step, great, you've all taken one step, you're happy. Now we're going to do the same thought experiment, but we're going to do it at the tip of the crack, okay? So in order to open the crack at the tip, the blue and green people, the middle and right people, they try to take a step. But that green person in the middle, they're holding hands with the person on the left, the yellow-orange person. And the person on the left is still connected to all the glass that's there. So, you can imagine you're taking a step, the person next to you holding your hands doesn't take a step. So what happens? You pull on them really hard. This is exactly what's happening in the glass. And in fact, the same thing happens on the other side of the crack. And the consequence of this is there's a huge pull right at the tip of the crack. And this huge pull is strong enough that with any little jostle or bump on the road, it will break the glass. And what's going to happen? The crack's going to get a little bit longer. And this process continues again and again at the new tip of the crack. And so it spreads out along its length. So that was about windshields. But what about the Earth? Remember, a fault is just a big crack in the Earth. So in some respects, the Earth is like a giant windshield, and a fault is like a crack in that windshield. An earthquake is what happens when that crack breaks. To sort of draw it explicitly, just like we had our cartoon there, this is our aerial view of the San Andreas Fault, and here's our cartoon of a crack, this time showing the crack as a fault with the sense of motion as was happening on the San Andreas. Okay, so you can imagine the same type of thing is happening. If you're standing over here and you sort of all take a step together, you're just moving and you're happy. But if you're at the very tip of the crack and you try to move, the person behind you doesn't move. And so it pulls really hard on that. And so at the very tip, you have this huge, huge push and pull that can cause more breaking. Okay, so let's now think about this concept for earthquakes in a bit more scientific detail. What I showed you was just these cartoon versions of what we think is happening for cracks on your windshield or faults in the Earth. And we as earth scientists, and this is me as an earth scientist, we have the knowledge and technology to develop physical computer models of these processes. Okay, well, we don't have to put them in computers, but the equations are pretty complicated. So practically speaking, we would never want to write them all down. So we put the equations into computers. And in fact, this is one of my primary areas of research, as you can see by this clearly not staged photo. Okay, this is definitely a staged photo. I sent this to the museum to be like, hey, use this photo for me being a scientist. But I looked at this and I was like, oh, shoot, that shows everything that I want to talk about in this talk. This is me working on computer models of faults in different settings on the Earth and trying to figure out which ones are likely to have earthquakes. So what can these physical computer models actually tell us? Now, one thing to just remind you, if you're a scientist, you probably know this already. And if you want to be a scientist, you need to know this. So any good model or theory is based on real world observations. If you ever run into someone who says they have it all figured out, but can't actually give you any evidence, you should get suspicious. Now, fortunately, figuring out how earthquakes are going to push and pull on the ground around them is really strongly rooted in real world observations. So if we want to, for example, develop a model of how the 4th of July earthquake might have affected the 5th of July earthquake, we can use observations like the ground shaking measured at the CSUB seismometer. This is the seismometer right on campus, and this is the record of the earthquake that occurred at that seismometer. We can use that to say something about what happened on the fault. Or we can go out to the fault itself. We're geologists. We go out into the field and we can measure how much the ground moved into the earthquake, So these scientists actually went out to the desert to make these measurements. And I was not there. I was not in California at this time, but I heard it was hot when this earthquake happened. I mean, think about July in the desert. This was like brutal field work, even though it wasn't like actual camping. It was really insane. So they raced out to make these measurements. They can measure how much the fault moved. And it's actually really good that they rushed out there, because just a few hours later, the road had been fixed. They could no longer see this measurement of how much the fault moved. So it's great for drivers that the road gets fixed. It doesn't have a fault going through it anymore, or an offset on the fault, but it's really terrible for geologists. So we need to get the California, whoever works on the roads in California, to slow down a little bit after a big earthquake. Okay. So we take all of these different observations and we can plug them into a physical computer model of what happened during this earthquake. So this is a model that I developed of the fault that broke. What is this showing? Here's the earthquake fault. Okay, that line there is a vast simplification of what those geologists measured in the field, what the seismologists measured in the shaking. And I just said, look, we're going to call it a single plane. So we have this earthquake fault. The colors in the background are from these physics-based calculations, the way we think a fault should affect the ground around it. When the two sides move past each other, how do they push in some areas? How do they pull in other areas? And we color them. The red areas are more likely to have an earthquake. Okay, so what does that mean exactly? You can see that the red regions are right off the tips of the fault. If the fault's in here, this line, the red regions are right off the tip. That's exactly what we saw with the crack on the windshield. So indeed, earthquakes are kind of like cracks on a windshield. But we also have these blue regions. And I didn't talk about that when I talked about cracks on a windshield, but when a crack occurs or when an earthquake occurs, there are actually a lot of regions that are less likely to have an earthquake. And we color those in blue, right? If you can think of, if the ground moves, if it releases all that pent up energy, then that section is going to be a little less likely to have an earthquake in the future. Okay. Now we want to go back and talk a little bit of history. This idea was applied for the first time here in Southern California. So this is kind of a weird looking map. I took it from a paper in 1992. This is a very famous paper. It's been cited hundreds and hundreds and hundreds of times. But in 1992, there was a big earthquake in Southern California, the Landers earthquake. Did anybody feel that earthquake? Is anybody around to feel that earthquake? Okay. I ask sometimes, but this was a while ago at this point. So either people weren't around, maybe they were young, things like that. But this was a pretty big deal, a large earthquake in Southern California. And it had a bunch of aftershocks, including a magnitude 6.5, the Big Bear earthquake. So some of these were quite damaging. And what they found in this study, you can see the colors. They're a little bit different than the ones I showed you, but there are these red areas and there are these purple-blue areas. Well, the red areas are where the scientists said, yeah, this is where earthquakes are more likely to occur. And the blue-purple areas, they said, oh, this is where earthquakes are less likely to occur. And what do they see? Most of the aftershocks occur right in the red areas, including the Big Bear earthquake. So the interpretation of these scientists was that the aftershocks were somehow triggered by the main earthquake. Okay, so this was the first idea. It was 30 years ago, and we've been sort of working on this ever since. Now, at about the same time that this earthquake happened in 1992, people were looking at another fault all the way around the world in Turkey. So for those of you who don't know where Turkey is, it sits right here, kind of in between Europe and Africa and Asia and Arabia. So Turkey's right here in the middle. And Turkey has a very famous fault in it too. You know, just like California has the San Andreas Fault, Turkey has a very famous fault too. It's called the North Anatolian Fault, and it runs right along the northern edge of Turkey. And in fact, you know, here is Turkey in yellow, and it's got the North Anatolian Fault. Here is California in green. I've tilted it sideways, so I've taken California from being north-south, and I've rotated it. And I've drawn the San Andreas Fault. And the San Andreas Fault and the North Anatolian Fault are like the same length. They've got the same sense of motion on them, the same speed of motion. They have the same size earthquakes. These are actually really, really similar faults. Okay, so the North Anatolian Fault, the better we understand that, the better we'll understand the San Andreas, and vice versa. This is why geology is a global science. Because sometimes, you know, you want to figure out not only what's going on your fault, but how a process works. So you want to look at all the faults you can all over the world. Okay, so we're going to look at the North Anatolian Fault, and we're going to look at the earthquakes on it over the 20th century, so the 1900s. Okay, so this is a fault that's had some big earthquakes on it before. In 1939, it had a pretty large earthquake, mid-sevens, and it broke a large area of the fault over here on the eastern end of the North Anatolian Fault. In 1942, the next section of the fault broke. In 1943, the middle section of the fault broke. You probably see where this is going, right? 1944, the next section of the fault broke. 1957, the next section. And in 1967, the section all the way over here on the left. Okay, so again, in the background, these colors represent those physical computer models. And we can see that there's red at the edges of each of these earthquakes. And each one propagated right along the fault to the west. So what do we see? Just like the windshield cracks. Okay, so instead of taking a couple minutes, this took a couple decades, but just like the windshield cracks, these earthquakes went step, 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 break, 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 all the way down the North Anatolian Fault. So if you had to guess, where would the next earthquake occur? What do people think? Yeah, right? If everything's stepping west, 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 we'd be like, yeah, it's going to be on the west end. It's going to be on the left side of things. So there's a town here called Izmit. And in 1999, this was, you can see this paper was published in 1997. So this study was before the earthquake, but in 1999, a magnitude 7.6 earthquake occurred. It was the next one in line. It killed 17,000 people in and around the town of Izmit, and it left more than 50,000 people injured. It was a huge, devastating earthquake, causing billions and billions of dollars of damage. You know, the pictures of destruction are almost total here in some cases, with, you know, buildings, even buildings that are standing, being severely, severely damaged. Okay, now this is a problem, because Izmit actually isn't even the big city in this region. The big city in the region is the next one down the line. It's Istanbul. And Istanbul is a city of 15 million people. It's the size of Los Angeles. And the North Anatolian Fault runs right through Istanbul, and Istanbul is the next city in line. So it has been, 20 something years since the Izmit earthquake, but that's the region that might be primed to go next. And Istanbul is not ready for this earthquake. So if this happens, when this happens, it is not going to be good. So these are things to be, very concerned about. This has real life consequences. Okay, so this is sort of how the idea of triggering got started, but we're now learning more and more about how earthquakes get triggered. So I'm going to show you some of my work on studying how earthquakes get triggered. I'm going to take you across the ocean. Okay, so we have been in California. I took you all the way to between Europe and Asia and Turkey. Now we're going to go almost to the total opposite side of the earth here. We're going to go to New Zealand. And New Zealand is this island country sitting in the Pacific Ocean. So it's east of Australia, it's north of Antarctica. It's a beautiful country. If you ever have a chance to go to New Zealand, it's truly fantastic. There's a reason they shot Lord of the Rings there, because it's got like every different type of landscape there. It's got mountains, it's got forests, it's got rivers, it's got everything you could ever want. I was lucky enough to go to New Zealand about a decade ago, and I would go back in a heartbeat. It's just a long ways away because it's across the Pacific Ocean. Okay, so in any case, there was a big earthquake that happened in New Zealand in 2010. It's called the Darfield Earthquake because it happened in the town of Darfield, New Zealand. And Darfield is about 15 miles west. Here's Christchurch here. I've just zoomed in on part of New Zealand. This is the city of Christchurch. It's got about 1 million people in it. Darfield is out here. It's about 15 miles west of Christchurch. And you can see the earthquake broke through this road, and probably from the scenery around here, you can tell that Darfield is pretty remote. Darfield is farms. I've actually been to Darfield, and I can tell you there are not many people living there. It is very, very rural. So you go from being in a city to being in the country very quickly here. So it was pretty fortunate that this earthquake happened outside of Christchurch, okay, because it didn't kill anybody. This earthquake resulted in 0 deaths. Yes, there was damage to the roads. Yes, there were damage to buildings. But even though it was a magnitude 7.1 earthquake, the timing of it and where it happened meant that nobody died in it. So that's great, right? Okay, so I just want to play this for you. This is an interview with a scientist from New Zealand, their equivalent of the US Geological Survey, and an interview a couple days after the earthquake about what they should expect going on in the future with the seismicity, because the earthquake hit and there were all these aftershocks. And let me just play this interview for you.
Given the fact that there are so many aftershocks, including that big one this morning, can you tell us a little bit about that one that shook us at about 10 to 8?
Yeah, it was quite strong in Riccarton Road where we accommodated.
Yes.
So we had a bit of a shake. Yeah, it is common. I think it was a 5.1 at the end. All the scientists were betting how big it was.
I bet.
There were some sixes being set there, but no, it's common. The Earth is still settling down. It's releasing still some energy, but it's usually common to have aftershocks, but not again a major shock. And in fact, in scientific terms, we call this main shock aftershock sequence of earthquakes, which means that you have a big one first, and then some medium-sized ones, a lot of small ones tapering off in a few weeks' time.
So how long will we be experiencing aftershocks and tremors? Is it something that we really don't know?
Well, there are studies in the world, and they are, it's common that they last for at least a few weeks after the.
So we can still kind of expect some in a few weeks.
Sure. You will be having a couple of weeks with common aftershocks for sure, and then less. Yeah.
Well, thank you.
Okay, so there was this idea here, and this was actually disseminated to the public, that these aftershocks, yes, they would continue for a little while, but over time they would sort of decrease and decrease and decrease until things were sort of back to normal levels of seismicity, which wasn't very much out in this region. And I don't mean to specifically pick on these people, but this was sort of the general consensus of what was going to happen at this point. This is what people thought, how people thought these sort of earthquakes worked. And this had deadly consequences. In fact, my PhD supervisor was actually in New Zealand when this happened. He was on sabbatical, and he was being interviewed in January of 2011 and said, look, there's the possibility for another aftershock or potentially a triggered earthquake to occur at some point. And the GNS Science, their USGS, basically sent him a cease and desist because they didn't want him to panic people. But it turns out, this is not earthquake prediction, but he was right. Another earthquake did happen. It happened on February 22nd, and this one happened right off the tip of the original earthquake right under Christchurch. So even though this earthquake was only a magnitude 6.2, which is still a pretty decent sized earthquake, it happened right under the city. And it did extensive damage to the city, to the point that even if you go to Christchurch today, and we're 11 years later now, even if you go to Christchurch today, there are parts of the city that are cordoned off. You simply cannot go to, they haven't cleaned it up yet. And it's not like New Zealand is a poor country. They have the ability to clean things up. It just did so much damage to so many big buildings. And sadly, it caused 185 deaths. So the collapse of the TV building, the collapse of many walls. This happened in a time when a lot of people were out or at work. And so it killed a bunch of people and severely injured hundreds more. So, my research when I started in grad school was on how these earthquakes occurred over time and how they might have triggered each other. So I, in fact, looked a little bit after the sequence and found that the areas near Christchurch, there were still some red in here. They might still be at risk of potentially triggered earthquakes. This was my master's thesis here that got published. And indeed, again, all hail the earthquake predictor. Okay, again, I'm not predicting earthquakes here, but the point is another earthquake did happen. And it happened exactly where we said it would. And it was not huge, but it shook people pretty hard. Now, a lot of buildings were already damaged. This wasn't going to do much more, but this would have done damage had it been the first one. So, we wrote another paper and thinking about, what's the earthquake potential looking forward for this region. Clearly, triggered earthquakes matter to this part of the world. Okay. So, and we see the triggered earthquakes, it's not just that they have to happen the day after or, a little bit after, they can happen years later. We saw this in Turkey, we see this in New Zealand. And in fact, these smaller earthquakes can be more destructive than their larger initial event. This is important to recognize. It's not just the big ones that do damage. It's the small ones. If they're in the wrong place, that's real trouble. Okay, so now I'm going to take you to the other side of the Pacific Ocean. So here's the Pacific Ocean. New Zealand's kind of around the back of the earth over here. You can see the USA is up here. If you go down to South America, along the western coast of South America is this long, skinny country here. That is Chile. And Chile has earthquakes all the time. It is incredibly seismically active. In fact, most of my PhD involved studying earthquakes that occurred in Chile because there were several of them that occurred during my PhD. So in March 2014, this is kind of when I was just ramping up on my PhD, there were 4 magnitude 6 earthquakes that occurred out here. This is offshore of northern Chile up here. And this is totally, totally normal for this region. This is expected. People were like, yeah, whatever. Okay, move on, next day, next thing. Okay, but if you kept a closer eye on what was going on, you might have been like, could this lead to anything perhaps? And in fact, on April 1st, just a couple of weeks later, there was a magnitude 8.2 earthquake. Now, a 6 might not be a big deal, but an 8.2 is a big deal anywhere it happens, even for a place that knows about and has earthquakes. And 2 days later, another major earthquake occurred. Okay, so we studied these, and it looks like, the initial earthquakes in March triggered the big one, which then triggered the next one. Okay, and we see this again with our computer models. We see where the big earthquake started at this star is in the red. Okay, so our computer models are telling us that this potential earthquake was going to happen or could happen. And so we see that not only can earthquakes trigger more earthquakes to occur, but potentially those follow-up events can be larger and sometimes much larger than the thing that triggers them. Okay, so that's important to recognize too. You know, even a small-ish earthquake like a 5 or a 6, if it triggers a 7 or an 8, that could be a big deal. Okay, so the last place I want to take you is Alaska. So it's back to the US, but it's not the mainland of the US. So California is down here somewhere. Alaska is way up in the North Pacific. And this had a series of earthquakes just in the last couple of years. There was a magnitude 7.8 earthquake last July, then a magnitude, I guess, 2 Julys ago, then a magnitude 7.6 in October, then a magnitude 8.2 in the last July. Now, these are big earthquakes, right? Fortunately, basically nobody lives in the Aleutian Islands in Alaska. The nearest big town is on Kodiak Island, 300 miles away. There actually are small towns here, particularly with native populations. So there's a town of Perryville that's like right next to the earthquake. And incidentally, one of the people at Penn State in the anthropology department is doing her PhD on with people in Perryville. And so there's actually a lot of sort of legends and things about earthquakes, and there's actually volcanoes here too, going back in time. It's this really interesting story, and it's connected to all the earthquakes. So we've been working with her on some really cool stuff, looking at sort of the local knowledge of earthquakes and comparing that to the science. It's very cool. But anyways, back to the triggering story. There's these 3 major earthquakes, the first one in blue, the second one in orange, the third one in green here. And the blue and green ones are exactly what we expect for this type of region, but the orange ones in here are super weird. Like nobody had seen any earthquakes like this before, ever. Super, super weird. Okay, so what do we take from this? Yes, there was triggering that went on, but the triggered earthquake was like totally different from the initial event. So not only can it, you know, occur in a weird place, it could be bigger, it could be smaller, it could be totally unexpected. So there's this whole range of possibilities that our modeling is just now starting to be able to explore. Okay, so back to California. Did the July 4th 6.4 trigger the July 5th 7.1? I've been kind of leading you up to this, but you know, we want to be able to say yes or no to this question. So what am I showing you here? This is a perspective view on the faults looking to the northeast. So you can see this is the July 4th fault, and it's sort of a 3D view down into the earth there. So this is the first one that shook on the 4th of July. Okay, so the colored fault is the one that broke on the 5th of July. And the colors indicate the calculations of whether things were pushed so that an earthquake is more likely or relaxed so that an earthquake is less likely. Now, the key thing is this star here. This star is really critical. That's where the July 5th event started. And we know that from those wiggly lines we saw earlier. And we see that squarely in the red region. So even though all this stuff over here might be blue, the fact is the July 5th earthquake started over here. And once it started, it was kind of like all heck broke loose, okay? So once it started, this whole fault, this whole long fault was able to just shatter the landscape, okay? So indeed, the 4th of July earthquake did trigger the 5th of July earthquake in this case. Okay, that's a nice story, but that's kind of in the past. What about looking forward? Could the Ridgecrest earthquakes trigger an earthquake on another fault? Well, there's the San Andreas fault, It's a little far away, but that's a major fault. We should be, worried about the San Andreas Fault. Another major fault in this region that gets a little closer is this thing called the Garlock Fault. And the Garlock Fault has had mid-sevens on it before, 7.5, 7.6 earthquakes. So maybe that would be something to be concerned about. There's some other areas with big faults and that have had big earthquakes in the past. In Walker Lane, one of the largest earthquakes in California's history occurred in Walker Lane in the 1870s. To the south is the Eastern California shear zone, the Mojave Desert, basically. This has a ton of faults that can have, this was where the Landers earthquake happened. So we can have sevens in here. So we have all sorts of places that we maybe want to be a little concerned about. Okay, so I ran these calculations last night so I could show them to you today. We can run these physical models and see what might happen. And what do we see? Parts of the Garlock Fault and some of the faults in Walker Lane are indeed in the red. Now, this doesn't mean these are imminently going to have big earthquakes. It is just something we want to be aware of as seismologists, as people who are trying to communicate potential hazards. All right, so how do we move forward from there? It's really important to just remember to be prepared that earthquakes are just an inherent part of living here in California. So what do you need to know? You need to know what to do when an earthquake hits. Get under something rigid, protect yourself, okay? Because it's not shaking that hurts you, it's falling stuff that hurts you. Same thing here, make sure your big stuff is secured to the wall, okay? So that stuff doesn't fall on you. Make sure you have, did I freeze? There I am. Okay, make sure you have a plan. Make sure you have, enough water and food to last you potentially for a few days if your power's out and your home's wrecked or something like that. And there's lots of information you can find on this online. So, this is something to really, be aware of, not be afraid of, but be prepared for. Okay, so I've got maybe about 15 more minutes before my slot is up. But I want to say a couple more things before I take your questions. And what I want to talk about is the idea of other things that could trigger earthquakes. Not earthquakes triggering earthquakes, but, human activities. So I'm going to take you out to China. China's right here. It's in Eastern Asia. So this is the Pacific Ocean. New Zealand's over here on the south side of the Pacific Ocean. The US is on the other side of the Pacific Ocean. This is China. And we're going to look at this dam in China, the Zipingbu. I don't know how to pronounce it. I'll have to ask Liaosha later how to pronounce that. But it's a big dam in China. And this dam was built and started filling in 2004. Okay, so you can see, this is a big dam. It's kind of from space. You can see all the water that's piling up behind it. But from space, it's a little hard to see the scale. This is a picture standing over here on the dams, looking out towards the fill. And you can see that this is a pretty substantial amount of water that's piled up in this dam. And that water pushes on everything around it. So much like you have earthquakes or cracks on your windshield that push and pull on the ground in certain ways, this water is also pushing and pulling on the ground in different ways. So in 2008, just 4 miles away from the dam, this dam pushed and pulled in the wrong way, triggering a giant earthquake. So this is people building a dam, causing the water to back up, triggering this giant earthquake. Now, this is an area that's had big earthquakes before. The dam didn't cause the earthquake, but the dam may have made this earthquake happen sooner than it would have otherwise. And this earthquake was devastating. It was a magnitude 7.9, so this is a really, really big earthquake, and it killed probably 150,000 people, both from the direct shaking and the total collapse of buildings, but also then from the huge landslides and then the landslide-related damming and flooding that happened later. So this was a devastating event triggered by the building of this dam in China. What about a place closer to where I've lived before, in the Netherlands? So in Groningen, there is natural gas production. that sort of ramped up in the 1980s. Okay, there's not really a good image of natural gas production, but those of you who know that it kind of looks like this. And this natural gas production, the extraction of this stuff from the subsurface, has led to things sort of settling out, and that has pushed and pulled on the ground in such a way that it triggers earthquakes and has damaged a lot of the old brick buildings sitting in the Netherlands. These are small. These are only up to about magnitude 3. But a magnitude 3 under your house that is not built for earthquakes is going to cause a lot of damage to your house. And currently the estimates are something like $6 billion of damage, which is not a small number. So last, I'm going to take you to Oklahoma. So here we are in Bakersfield. We're going to go all the way over to Oklahoma here. And this is a place where, again, there's a lot of natural gas production. And when they're taking this stuff out of the subsurface, there's a lot of water that comes with it. And that water is getting pumped back into the subsurface because they don't want the water. So since that wastewater injection began, Oklahoma now has more earthquakes every year than California. Now, I don't think this is actually still true. I haven't plotted it for myself, but I think if you ask most people in the US where the most earthquakes occur, they would be like California, or if they knew better, they might say Alaska. But the answer right now is Oklahoma. Most of these earthquakes are relatively small. We've got a few 5s in there, maybe a 6. But again, doing substantial damage to towns and communities in Oklahoma, producing billions and billions of dollars of damage. So the point here is that it's not just earthquakes that can trigger other earthquakes. It's really anything that pushes and pulls on the ground and is near a fault. Those can cause those faults to pop off and a lot of damage in those nearby regions. So that is all I've got for you today, and I think I've got a few minutes left for your questions. Thank you. Okay, so question in the chat: do these oddball or unexpected earthquakes soon after significant quakes tend to follow previously unknown or underappreciated faults? Do they tend to? Probably not. I mean, there's a reason that they're unusual, and they're unusual because we haven't seen them happen a lot before. But I'll be honest, we're learning a lot about earthquakes every day. And we just don't have a lot of the record of earthquakes going back in time. So, if earthquakes happen every 100, 200, 300 years, we've only got really good records of them going back, say, 50 years into the 60s and 70s. So we might be missing a lot of earthquakes. So we think they're odd, but maybe they're just things we haven't seen enough before. We haven't been looking for long enough. So it's hard to answer those types of questions, but we see a lot of examples where these odd earthquakes do happen, so we need to be prepared for them. Okay, so there's a question about what was the biggest earthquake ever? The biggest earthquake ever was a magnitude 9.5 earthquake in southern Chile. So we were talking about Chile earlier. If we go back here, take you back a little bit to the South Pacific, Southeast Pacific. Okay, so the biggest earthquake ever broke the southern part of offshore of Chile. Giant earthquake, magnitude 9.5. In fact, it was so large that one of the events that people think it triggered occurred in 2010, was a magnitude 8.8 earthquake on its own. So one of the earthquakes triggered by this giant event was still one of the largest earthquake ever recorded. That's how big it was. Okay, so when these multiple earthquakes in an area happen, are they typically on another fault system adjacent to the original fault where the original earthquake happened? Sometimes yes, sometimes no. So let's take you to this example here. Well, this is actually one of the examples where we had no idea any of these faults existed in New Zealand. If you had asked anybody before 2010 whether there were faults with the potential for big earthquakes out here, they would have just laughed at you and said, no, no, no. The one to worry about is the one going along the western coast here. There's big mountains in the South Island of New Zealand because there's a big fault there called the Alpine Fault. And that's capable of magnitude 8 earthquakes. So that's what everybody was worried about. They weren't worried about the earthquake that could be under their house. So sometimes these multiple or triggered earthquakes are on random unknown faults. A lot of these are, you can see them going off in all sorts of weird directions. Whereas going back to Turkey, they were all on one fault. They were all on the North Anatolian Fault. So again, it sort of just depends on which situation we're looking at. Okay, so there's a question about what was the biggest tsunami from an earthquake. And it depends exactly what you mean by the biggest tsunami. If we're talking about the highest wave, the waves in the 2011 Japan earthquake, in some cases reached a little bit under 40 meters. 40 meters is about 130 feet high. So, you know, these waves would have gone, in fact, did go up into the mountains such that they like went up some mountain streams and they displaced these big mountain lakes. So now these lakes, even today, 10 years later, are saltwater because the ocean came in and displaced all the fresh water in these lakes, you know, 120 feet up. So the lakes are higher than that, but the tsunami coming in was 120 feet. So really, really big, scary waves. And I can talk about tsunamis maybe next time. That's what I'll do. I'll talk about tsunamis.
Larger question about the Walker Long Valley faults. Could some of that motion have sort of, well, I hate to use the word displaced, be displaced motion from the San Andreas? In other words, the crust broke there instead of along the San Andreas Fault? Or that section of the San Andreas Fault?
Yeah, so we're asking about, you know, here's the San Andreas, and everybody sort of has this image in their mind of the San Andreas as being kind of the fault for California, but really the plate boundary system in California really extends from basically the coast of California, because there's mountains actively deforming here, all the way to Nevada. It's not really until you're past Nevada that you're really on North America. And so the San Andreas takes up some of that and has big earthquakes, but Walker Lane also takes up some of that. So Walker Lane has, you know, mid-7s to magnitude 8 earthquakes occasionally because indeed, you're right, that motion is sort of partitioned, is separated onto those two fault systems. Now, it's interesting that you know, Kern County, the Valley, and the Sierra Nevada really don't have many earthquakes. So there's something special about what we call the Sierra Nevada or Great Valley Block. It's somehow very strong. It doesn't want to get broken. It doesn't want to have faults in it. So everything that's deforming is kind of shaping itself around that block. Which is why you get Walker Lane, the Eastern California Shear Zone, the San Andreas Fault sort of forming these structures around it, because this region where we're sitting right now is actually relatively strong. Yeah, so predicting earthquakes is not something we can do, unfortunately. When people say predicting, they're often talking about when it's going to happen, and that's not something we're capable of doing yet. Now, maybe someday, but right now we're not actually able to say, yeah, an earthquake's going to happen on Wednesday at 6 in the afternoon. So there are some technologies to monitor earthquakes better, or maybe even warn people that big shaking is going to come. But still, we're not at the point of predicting yet. But, you know, that's the holy grail. So maybe we'll get there someday. Okay, so is it of relevance if after 2 significant earthquakes, there are still a lot of aftershocks, even 2 or more years after the original earthquake? Yeah, I mean, I think potentially, I think that level of activity, people have looked at this and said, oh yeah, this high level of activity is probably an indicator that this sequence isn't quite done yet, that there could be something happening. And in places like, the major faults like the San Andreas or the North Anatolian fault, that's not what we see. But in some places, these earthquakes do have aftershock sequences that seem to last sometimes for decades, maybe even centuries. Now, those aftershocks are very slow after centuries, but the level of activity is higher than before the earthquake for 10, 20 years, as long as we've observed. So indeed, that could be an indicator of, potential triggered earthquakes happening. So, great questions.
I've allowed folks to unmute themselves. So if there's anybody that was unable to post their question in the chat window, or by the way, I did finally post the donation link. If at this point, if you'd like, you can unmute yourself and verbally pose your question.
Yeah, you're welcome. Thanks for coming.
Are you still there?
Yes?
Yeah.
Oh, okay. The water fresh water being displaced by salt water was something I'd never heard of. What are some of the other unusual things that tsunamis and earthquakes make happen that I've never heard of before?
Oh boy, I don't know what you've heard of, so that could be.
I just know the typical stuff where the destruction in cities and mountains.
Oh boy, you're just gonna have to take my class to hear about some of the weird stuff. But there's all sorts of sort of strange events that happened. With the last big San Andreas earthquake caused trees to be uprooted in Kern County. Fish were thrown up on the banks from the river and so yeah, I mean, these things cause all sorts of weird effects. Sometimes people talk about weird sounds. Sometimes actually earthquake lights are even a thing in some cases, not all. But yeah, there's all sorts of liquefaction and geysers. Yeah, there's all sorts of things. And come take my class and I'll tell you all about them.
More details on your class? Where would I find?
I teach at CSUB, so it's a class at the university, but I'm happy to talk more about earthquakes. Feel free to email me and we can chat about it.
Can you explain more about earthquake lights?
Yeah, it's going to take a little time, and I don't actually have that time right now, but feel free to email me and we'll talk about them. Happy to do that. Okay, so I actually just got a question as a direct message when the last major activity on the Garlock Fault, and I would have to look that up. I did look it up before my last talk and totally forgot the answer to it, but I will have to look that up. It's recent geologically, but not recent for people.
You want me to post your email in the chat, or would you rather?
That'd be great. Yeah, you can post in the chat, or you can just look me up, Matt Herman, CSUB. You'll probably find me. And please feel free to email me. I'm happy to talk about earthquakes.
Okay, I think that's about it. We're out of questions and we're effectively out of time. Thank you, Dr. Herman, for your time today and for sharing your knowledge with us. The museum would love to have you back soon.
Yeah, thank you for the invitation, and I'm looking forward to being back.